Okay, now we're looking at the conservation momentum, which basically says that the momentum before collision must equal the sum of the momentum after objects interact with each other. Remember, this is a symbol for sum. P is the momentum. So we could write that as m1v1 plus m2v2 must equal m1v1 plus m2v2, where the right side is after interaction. That's supposed to be after. After, and this side is before. So that's really all there is to conservation. Just like conservation of energy, the sum of the momentum before must equal the sum of the momentum after. So there's three types of general interactions. First is elastic, which looks just like the conservation of energy. Kinetic energy is also conserved during elastic collisions, and that is when P1 plus P2 equals P1 plus P2 after. And if you think about elastic, they bounce off of each other. So the momentum is two objects are separate before they collide, two objects separate after they collide. In inelastic, they're not bouncing, they tend to stick together. So you have two objects that are initially separate. So this is before. And then after they collide, they tend to stick together. So on the other side, we're going to put the masses together, so m1 plus m2 are stuck together, moving as one final velocity. And here, note that the kinetic energy is not conserved. So the sum of 1/2 mv squared on this side does not equal the sum of 1/2 mv squared on this side. And that's important to note, and we'll look at that in an example. In inelastic collisions, there's partial inelastic and perfectly inelastic, depending on how well the two objects stick together. There's also a third type of interaction where two objects separate or there's an explosion. So you step off a boat or you have fireworks. So the sum of all the individual particles added back up equal each other. Again, kinetic energy is not conserved. So on this side, you have all the different masses, however many there are, all moving at one speed, or not moving at all, must equal then m1v1 final plus m2v2 final plus m3v3 final. Recognize they're all based on really that first part of conservation of momentum. They're just whether they're together or separate after they interact with each other. So let's take a look at an example. So in a game of marbles, a 0.1 gram marble traveling east at 2 meters per second collides with a second marble of mass 0.2 kilograms at rest. Don't forget to look for the words of at rest. After the collision, the first marble stops and the second marble moves to the east, looking for the final velocity of the second marble. So set it up. M1 is equal to 0.1 grams. M2 is equal to 0.2 grams. V1 initial is 2 meters per second east, and V2 initial, V1 final, V2 final. So the second marble is initially at rest, so its speed is 0, and the first marble stops afterwards, and we are looking for that final velocity. So it's an elastic collision. They're separate initially, and they are separate afterwards. So that sets us up with m1v1 plus m2v2 must equal m1v1 final plus m2v2 final. Since this initial speed of this one was 0, we can cross that off. And since this final speed of velocity 1 is also 0, that can get crossed off. So 0.1 grams times v1 of 2 meters per second must equal m2, which is 0.2 grams times v2 final. Now, because my units are both in grams, I don't have to convert those. The units will cancel out, and I'll be left with the velocity. So I don't need to convert here. So if we solve then for v2, we'll divide by 0.2 grams. Divide on this side by 0.2 grams. And we end up with grams canceling grams. That becomes 1/2 of 2, which is 1 meter per second. So that's the v2 final. Which, going back, makes sense. If we double the mass, when we have these two momentums must equal each other, this velocity has to be half of that one, since this is twice the mass. All right, another example. Okay, in example 2, we have an 80 kilogram person stranded in the middle of a frictionless ice rink holding a second mass of 2 kilograms. And he's unable to walk to the edge of the ice rink because it's frictionless, and he throws his book 20 meters to the north. So both of these people originally have a velocity of 0. We want to know the final velocity of the person, and the final velocity of the book is 20 meters per second. So you can picture them, they're both sort of standing out in this frictionless thing. He throws the book this way, and he would slide backwards in this direction. So we want to know what is that velocity. So initially, we have a situation where the two masses are standing there together, moving as one, and that must equal then the m1 v1 plus m2 v2, and these are both final velocities. Since they're not moving initially, this whole side goes to 0. So we have 0 is equal to 80 times v1 final plus 2 times 20 meters per second. So if we subtract off, we have a minus 80. v1 final is equal to 40 kilogram meters per second. And solving then for v1 final, we get that is equal to a minus 0.5 meters per second. And because it was going north, we will be going south. So there is our v1 final. And then for part B, that's part A, this is part B. Does the kinetic energy of the book equal the kinetic energy of the student? Well, I'm going to make a prediction that it is no, but let's verify that. And I'm going to let you finish this off, but I'll get you started. So the kinetic energy, again, is equal to 1/2 mv squared. The initial kinetic energy is equal to 0. So if we look at the kinetic energy of the person final, well, that's going to equal to 1/2 mv squared, which is 1/2 mass of 80 times the final velocity of a minus 0.5 meters per second squared. So the final kinetic energy of the person is 40 times 1/2, which makes it a minus 20 joules. And the kinetic energy of the book final is equal to 1/2 mv squared, which is 1/2 of 2 times velocity of the book was 20 squared. So 1/2 of 2 is 1, and 20 squared is 400, so that's a positive 400 joules. So before collision you have 0, and on the other side you've got 400 minus 20, so those don't equal each other. So conservation of kinetic energy does not hold.